Okay, we are going to talk about the graphs of rational functions. We're actually going to start by doing two of them right off of rational functions sheet 2. If you, most of you would have done this in algebra 2. So yes, you have seen this worksheet before. And I'm going to do number 2 and 4. So number 2 looks like this. Squared minus 1, x cubed minus 2x squared plus x. So to do this, we know that we can't divide by 0, and that's going to produce vertical asymptotes. So on this, it asks you for vertical asymptotes. This one actually asks you for horizontal. We're going to start classifying them as end behavior asymptotes because this worksheet has all horizontal asymptotes, but end behavior asymptote I'm going to call EBA because we will do some that aren't horizontal. We're going to talk about holes. We're going to talk about roots. And I guess I didn't ask you for it on the worksheet, but I also want you to be able to identify the y-intercept. And we're going to identify all of this by hand before we go to the graphing calculator. So I'm going to start doing this by factoring. Factoring x squared minus 1 is x plus 1, x minus 1. It's the difference of squares. Take the square root of x, because squared gives me x, and the square root of 1 gives me the 1s. My bottom, I'm going to start by factoring out an x, because it's a common factor to all of them. And then I can factor the rest of the denominator into x minus 1, x minus 1. Now, to simplify my life, I'm going to cancel out an x minus 1 from top and bottom. Zeros of the denominator. Now, what's left, zeros of the denominator, zeros that are left in the denominator, become my vertical asymptotes. Well, x is 0 when the x term, this guy, is 0, the whole denominator becomes 0. For this one, x minus 1 qualifies when x is 1. And I'm going to come over here, and I'm going to draw my graph. And then I'll start graphing it. I'm going to plot my vertical asymptotes in red here. At x equals 1 is a vertical line at 1. X equals 0 is a vertical line right up the y-axis. My end behavior asymptote, I look back at my original, and I take this, the largest term over the largest term. I'm going to say y equals x squared over x cubed. And I can reduce that to 1 over x. As x gets large, so x goes to infinity, that becomes 1 over something large, which is approximately 0. So I'll plot my horizontal asymptote. End behavior really means just as x gets large. So as I go to the ends of my graph, or my limits as x approaches infinity or negative infinity. Okay. Holes. This one does not have any holes. Roots are zeros of the numerator. So I take my numerator, what's left of it, set it equal to 0, that's negative 1. I'm going to make my graph be purple. Yes, you can cross a horizontal asymptote. You cannot cross a vertical asymptote. My y-intercept. Y-intercept, I'll show you how to get on the next one. This one does not have a y-intercept because the y-axis is a vertical asymptote. You can't cross it, so you can't intercept it. So To resume my, or to make my graph, I'm going to go to my graphing calculator, and I'm now going to plug this in. I put my asymptotes on the graph by hand to help me understand what I'm doing. So I go to y equals, I've got this nice 84 that lets me do this fraction thing. If you have one that lets you do it, I recommend using it. If you do not, I'm going to show you how to do it without. I'm going to add an extra set of parentheses. Well, I don't need an extra set on top. If I have parentheses like I do in number 4, I'll add an extra set on top. So I'm going to do x squared minus 1, close my parentheses, divided by my denominator. I'm just entering the original because I can. X to the third minus 2x squared. Part of the reason I'm doing the original is just in case I made any mistakes factoring or I screwed something up, it'll show me. I hit enter. There's my graph. I'm going to go to standard zoom, which is zoom 6. And I get this. It's a little interesting looking. For a second here, I'm going to show you because this is funny. I'm going to zoom in on the Y's a little bit. You'll notice here, this actually breaks below the line. This one's above. I'll go back to my standard zoom. So I know that this branch here is going to pop below the line. So I'm going to sketch my graph. I gave graphs on the thing. Go back to my whiteboard, sketch my graph. So this actually comes like this, and it hooks back at it. And it goes up and through. Somewhere down here was a little U there. And then I had a branch over here. Notice that in every section cut off, section 1, 2, 3, there was a branch of the graph. Okay, I can't cross my vertical asymptotes, but I must have 3 branches because I've got 3 sections. If I don't see one, I've got to adjust my window on my calculator. So we're going to look at branch 2, or problem 4. It's going to show us a couple other interesting things. This one's kind of nice because it's given in factored form. This one will be a little harder to enter on the calculator, though, unless you have a calculator that allows for the fractions. Those are the 84 CEs, the Inspires, and I'm not sure about the Casios. Probably actually on the Casios. The old 84s are, some of them have it, some of them do not. But it's alpha and the key right next to alpha. So, little trick on this. First thing, x squared minus 4 does factor. So I probably better factor that. X plus 2, x minus 2. I'm also going to give a partially expanded. Instead of multiplying it all out, I'll just multiply my firsts. My 3x times x on top gives me 3x cubed. Because remember, I used that in finding the end behavior asymptote. I'm also going to multiply out my lasts. Negative 5 times 7 times negative 2 is plus 70. Okay. Multiply out my firsts on the bottom gives me x times x times x is x cubed. 2 times negative 2 is negative 4 times 3 is negative 12. So my vertical asymptotes and behavior asymptotes roots, poles, y-intercept. I'll make my graph. I'm making the x-axis a little bigger intentionally. So, first thing I look for is what cancels out, if anything. X minus 2 cancels out with x minus 2. That means I have a hole where x minus 2 equals 0, which is x equals 2. I'll show you how to graph that later. The rest of my denominators, x plus 2 and x plus 3, give me zeros when x equals -2 and -3. I'll go ahead and plot those right on my graph. They're kind of close together. My end behavior asymptote. I circle 3x cubed over x cubed gives me 3. So y equals 3. I'll plot that on my graph. My roots. Going to be my numerator. 3x minus 5 equals 0. That's x equals 5 over 3 when I solve it out. And x plus 7 equals 0. That's -7. I'm going to go put those on my graph. 5 over 3 is here. 4, 5, 6, 7 is here. Did get that far. My y-intercept is found by the 70 over -12, which I can reduce to -35 over 6, which is just a little less than 6. 3, 6. Now, from experience, I know what this is going to look like, but I'm going to show you again with the graphing calculator. So to enter this, I'm going to start by clearing this. Yes, on this calculator, I would use alpha and the X button because that gives me a fraction. But if I didn't have this calculator, I'm just going to enter a second set of parentheses around my numerator. So I got parentheses, then parentheses, 3x minus 5. Close my parentheses, new parentheses, x plus 7. New parentheses, x minus 2. And yes, even though the x minus 2 cancels, I'm going to put it in there. Close my set of parentheses for the numerator. Divided by second set of parentheses for the denominator. Yes, I'm going to use the unfactored x squared minus 4. It's a little less to enter. And x plus 3. Close my second parentheses. Hit enter. And was on Zoom 6. So I can see a couple of things here. And I'm going to go put them on my graph. I see a branch here. Yes. Do they always go towards the asymptotes and eventually get there? Yes. It usually doesn't cross the horizontal asymptote unless you see it crossing. And there we have that. But I noticed that section 2 doesn't have anything in it. So I don't know where that is. So I got to go to my calculator and find it. Back to my calculator, which means it should be somewhere. So I got to look at my y's and zoom out. Because both of these are going down as I approach those vertical asymptotes, it's probably high. What am I going to do? I'm going to take my y's. I'm just going to add both, though. I'm going to go both ways. And let's go to -100. I can't use that, but can't use the minus button. It doesn't work. And I'm going to go down to 100. And we'll see. Nope, not big enough. Let's do 500. And 500. Oh, there I have it. So how am I going to draw that on a graph? Because that's up like 250. I could find the actual minimum. I'm going to use a little break symbol here in my graph to note that I'm breaking here and then going up to about 250. You could find the minimum just like you found any other minimum. And that just hooks up like that in between those asymptotes. So it's really tight. Looks sort of like a parabola, but it's definitely not a parabola. Parabolas keep getting wider and wider. This does not. Okay, we're going to go to the book now and take a look at example 2. Example 2 is talking about transforming this function and using translations. So if g of x, well, instead of y, we'll say f of x. If g of x is this function, I have a vertical stretch of 2 and a horizontal translation of 3 left. I can think of that in my function form as g of x equals 2 times f of x plus 3. That one's nice and clean. H of x is a little less clean. Right now, it doesn't look like it's in the 1 over x form. I've got an x on top and bottom. So I didn't just multiply by something. So in order to do this, I'm going to divide, and I'll use synthetic division. Why use regular division when I can use synthetic? 6, -1 is the remainder, so I've got 3 minus 1 over x minus 2, because that's my denominator. Or I can look at this as -1 over x minus 2 plus 3. So I'm shifting. I mean, actually, first I reflect over x-axis for the negative here. That's reflect over x-axis. Shift right 2, up 3. For the minus 2 is right 2, up 3 for the plus 3. And that's that graph. Okay, that is example 2 from 2.6. Let's take a look at example 3 pretty briefly. We have x squared plus 2 over x squared plus 1. So again, I'd look at what I was doing with vertical asymptotes. I don't have any because x squared plus 1 is never equal to 0. There's no real number that I can put in for these graphs. I'm only looking at real numbers to get 0. I can do a horizontal asymptote trick and realize that it's going to be 1. So I've got a horizontal asymptote here at 1. If I plug in 0, I get 2 over 1, so that tells me a y-intercept. at 2 here. And this graph actually just looks like this. It should be symmetric. There's a better drawing in example 3 in the book. Okay. Another rational function, example 4. F of x equals x cubed over x squared minus 9. So I'm going to do this a little bit. X plus 3, x minus 3. I'm also going to put in this little plus 0. It's going to help me later. So, vertical asymptotes. 3 and negative 3. End behavior asymptote. Y equals x cubed over x squared. This is going to get me an approximate. This is not an exact end behavior asymptote, but it will get me close. We'll show to get an exact one later. X. Y equals x. That is a line with slope of 1. There's not any holes on this one. Nothing canceled out. Roots. Well, the zeros of the numerator are x equals 0. The y-intercept, well, if x equals 0, that's also going to be 0. But I can take this numbers. This is why I put the 0. 0 over 9 is also 0. So to sketch my graph, 1, 2, 3. 1, 2, 3. I take my vertical asymptotes and I put them in. Take my end behavior asymptote and I put that in. And then I go to my calculator. And because I've looked at the book, the calculator is going to show you something like this. Plug the original into your calculator. Make sure you see this. Pause if you need to while you do it. And you see this. It's got to go through 0, 0. That is both the x and y-intercept. And that is my rational function. We're going to talk about a function analysis of a rational function. I believe there's one sort of like this on your test. So make sure you pay attention to this. The test is coming up in, another week or 2. But be aware that a function analysis of a rational function, I'm pretty sure, is on there. So I probably want to actually start by making my list. Vertical asymptotes. Well, let's factor. Take a 2 out of the top. And that is going to end up as 2, x plus 1, x minus 1. And I can factor the denominator into x plus 2, x minus 2. Which these do not cancel out. So my vertical asymptotes are x equals 2 and negative 2. I do not have any holes. My end behavior asymptote, I'll take that. That's probably the other thing I really need before looking at the graph. And that's 2x squared over x squared, which is going to be 2. So function analysis has a domain. Domain is going to be everything except those vertical asymptotes. Must be written in this form. Negative infinity to negative 2. Again, I'm working my way across the number line. I start on the left with negative infinity, go to negative 2. I do not include negative 2. I go negative 2 to 2. Again, I do not include 2, and I go 2 to infinity. So I'm working my way across the number line. I need to look at the graph here before I start going range and other things. So let's take a look at our graph. So we go to our calculator, clear out the last one, and this one I'm going to enter this way. 2x squared minus 2 over x squared minus 4. Whoa! Oh, I'm not in standard zoom. That's why it's so crowded together. Okay, so I can see this. It appears that it does not cross 2 on the range. These appear to just be coming down. There's nothing weird in this one. Oh, before I give the range, I need to find the top. So I'm going to find the top because there might actually be a gap in the y's. It kind of looks like there is. I'm going to find the maximum. This maximum of 1.856 e negative 6, that's 0. That's just the calculator not being quite on. So the range here, the range though is a little tricky. There's a little gap in the y's from 1/2 that top point. So it comes from the bottom up, negative infinity to 1/2. That point is included because it's part of the thing. But then it has a gap again until it goes over the horizontal asymptote of 2. And it will not get to its horizontal asymptote in this case. Most of the time, that's the case. Continuity. You can either list as the same as the domain, or you can say x is not equal to -2 and 2. It's continuous everywhere else. This graph is increasing. So it looked like this. And again, I'm going to map increasing based on the x coordinates, not y. So it's increasing on this leftmost branch, negative infinity to -2. I have to cut it there because there's an asymptote. It's increasing again for this part and starts going down after 0. So that is -2 to 0. I'm going to include 0 because it increases all the way through 0. Afterwards, it starts decreasing. 0 gets included in both to +2. And the rightmost branch is also decreasing 2 to infinity. Symmetry. This one actually looks like it has y-axis symmetry. And with the squareds, it would make sense. Don't give me a yes or no. Give me a which symmetry, y-axis origin. I guess it wouldn't be a function if it has x-axis. So don't tell me that because then it wouldn't be a function. Boundedness. This is unbounded. There's no absolute top or bottom. Max min or extrema is what I like to call them when I list this on your tests and quizzes. It has a max at 0, 1/2. Asymptotes. There's only, I'm going to spell asymptotes correctly. 1s an asymptote. It's been too long, I guess, since last year. Asymptotes are x equals -2, x equals 2 for the two vertical ones, y equals 2 as well. And then I have end behavior. And I need to write this in limit notation. And I'm going to try to spell behavior correctly. Limit as x approaches -infinity. And I don't want to write out the whole function, so I'm just going to write f of x since that's its name. Cannot be blank. And it's going, the end behavior asymptote is 2. That's where it's going. Limit as x approaches infinity, positive infinity, is also 2. Okay. That is a function analysis on one of these. Let's talk about finding an end behavior asymptote better than just the shortcut. So here's a new function. This is example 7. My shortcut trick was take the largest over the largest. X cubed over x, and that's x squared. So it's going to be approximately x squared. If I want to know what it actually is, I use synthetic division. So I'm doing x cubed minus 3x squared plus 3x plus 1, and I'm dividing that by x minus 1. Lucky I can use synthetic. I suppose I could use long if I couldn't. So 1, 1, -2, -2, 1, 1, 2. So the end behavior asymptote that I'd graph is actually this. This is a parabola with a vertex at roughly about 1, 0. It's very close to 1, 0. This is technically my end behavior asymptote. So this was a parabola centered at 0, 0. If you start to get out far, you can't tell very much what it is. This graph ends up looking like this is my end behavior asymptote. I have a vertical asymptote at 1. And my graph looks kind of like this funny thing right here. And that is section 2.6, rational functions.